So those, let's say, are the original Z coordinates and Poisson solved Z coordinates. Would be those, no, just Zm. Okay. And it'll be interesting to see what happens if I replace the Z coordinates of the mesh with these Poisson solved Z coordinates. Okay, so I'm going to create V of all P in comma 2. Those are similar to my original Z coordinates, and I'm going to go ahead and replace it with Zn, and I can now plot. So I have no idea what to expect, but let's see what I get. So what I've done is this is my original mesh, or at least this is our original mesh. We had this camel with some XYZ locations for each of the vertices. So we have solved a Poisson problem in which we have used the Z coordinate as the boundary condition. So we are expecting that the solution gives us some new updated Z coordinates, and those are called, I don't know, Z interiors. And so once I've solved this problem, I'm going to replace the original Z coordinates with these updated Zns, and I'm going to try plotting the mesh to see what I get. So that's what has happened. So this is kind of related to the smoothing. If this, okay, so I don't know how many of you read all through the notes from that I posted. You have the heat equation, and in the, so the heat equation is a time dependent partial differential equation, which involves the Laplacian. In the limit that time goes to infinity, you end up with what's called a steady state. And the steady state limit of the heat equation is the Poisson equation. Okay. So if I want to smooth a mesh, I would run a couple of steps of heat equation. But if I now, instead of running a couple of steps of heat, which will smooth it, if I solve the Poisson equation, this is like running the heat equation to its completion. Okay. And in this process of smoothing, in this case at least, it has sort of, I don't know, what do you call it? Has it compressed? It's not compressed it. It's so over a, I mean, it's not deformed it. It's trying to take it the smoothest. So this is like a, so, and this is done only on the Z coordinate. If I do it on the X and Y coordinate, this shape topologically is like a sphere with a little slice cut off. Okay, it's like if I take it, think of it like if I had clay and I could fabricate this shape, I could start with a little pot-like structure and then sort of sculpt it, or using clay, I could fabricate a head like this. So topologically, this is like a sphere with a slice removed. And in the process of smoothing, what would happen is all the structures that you see, I mean, if you smooth it for a little bit, all the noisy features will go away. But if you keep smoothing it, all these structures that you see on this camel will disappear. You'll get like a pot-like structure with a neck. Okay. And if you continue smoothing, this is what happens. The heat equation sort of keeps pushing this pot down. In the end, you'll get something that's flattened completely. And that's why you see this at least flattening in the Z direction has led. There's still something in the XY direction. We haven't done anything in the XY direction. This has flattened it completely in the Z direction. If I did the same thing with X, solving a Poisson equation instead of with the Z coordinates, if I did this with X coordinates, Y coordinates, and replaced the mesh with not just the updated new Z coordinates, but new updated X coordinates, Y coordinates, you should get a thing that's close to a point. It should collapse it on this. This has collapsed it in the Z direction. It should collapse it in the X and Y directions as well. And you should get something close to a point. Okay. Or at least maybe in this case, I mean, even this ring will shrink and you'll get because in the limit that kind of keeps driving it down to close to a point. In this case, it'll be like a small ring, I think, because there is still the topology of the circle. But this is like in the limiting case. But if you don't want to do this, you could smooth the mesh. And let me try and see if I can.
So this tapering is because of the boundary.
There is a boundary condition. Yeah, you're right. So that's exact. Thanks, Aradhya. Yeah. Do you want to try explaining it once? Here is a. Okay. So yeah, that's good. That's a good point. So let's try doing this for a different mesh which has no boundary, maybe. Yeah. How much time we have? 23 minutes. Yeah. So let's do it for this Cheburashka. Huh? Yeah, this is a water type mesh. It'll collapse it to a point. Yeah. So let's see. So this is a water. This is a mesh with no boundary. So the boundary condition is going to be weird. There's no boundary condition.
This in the backend solve it iteratively, or
It just is a direct solver. It's a direct solver. Yeah.
because then via the number of shifts maybe could control to what scale.
Right. So let me try doing the heat equation here. Therefore, what you're saying. So let me load this. Let me obtain the Laplacian on it. Now let's run heat equation on this. And I'm going to run this. So I'm going to solve Laplacian U. Let me try to make it like this. Laplace.
You could use double count to increase the size.
So Laplacian U at some n is going to be equal to U of n minus 1. Okay, so this is going to be my heat equation that I'm interested in solving. There is going to be an initial condition. So let's say with initial conditions, U of 0 equals x. So what I'm going to do is successively, like I'm going to think of this as, I'm going to first start with the x coordinates, y coordinates, z coordinates, and keep running the heat equation for each of these coordinates a little bit, and starting with the original x, y, z, and we'll see what happens to this mesh as a result. Okay, so let's run this for some t time steps. And we are going to assume that each time step is 1 unit long. That's the assumption that I kind of made here. What else did I do? I need partial u by partial t. Okay, this is quite not it. So the heat equation would be partial u equals something like back partial u over partial t which I'm going to approximate as un minus un minus 1 by delta T. So that's going to be my heat equation. So if I move this un term to the other side, I will get I minus L times un equals to n minus 1. Okay, where L is the Laplacian. Okay, so the top is the heat equation. It's technically just this. And I'm gonna use U as the UN. Okay, I hope you folks took a read or read a little bit of the notes, because I did post a bit of this. So I can set delta T to be 1 and move 1 minus Laplacian here. And since there's a negative sign, I'll throw that in and make this 1 plus L. Okay, so 1 plus L UN is UN minus 1. And I'm going to be wanting to solve this problem at every step, starting with this initial condition. So let's run this for some T time steps, and let's set T to be 10 time steps. Okay. So I already have the cotangent matrix. I have to create a np dot. Okay, I need to create a sparse identity matrix of the size L dot shape of 0. Okay, I did not include SciPy dot sparse as SPRS. Okay, I have that now for ion range of time identity matrix for ion. Okay, so 15 range of time. I'm gonna solve x is equal to sp. So I need my x is v of this, y is v of that. And now I'll do the heat equation iteratively. So x is going to be sp solve I plus L, and this is going to be just x. And we'll do that for y and z as well. Okay, and now I will assemble all of this. V is v of 0 is x, v of 1 is y, z, and then I'm gonna do 0 time steps to see that nothing has changed. So that's my original mesh. Let's try plotting this now. So let's, yeah, I need to run this again. Yeah, I'll run this again. That's my original mesh. Right now I've set the time step to 0, so nothing should happen. And if I look at, okay, look at the mesh again, I get the same thing again. No, nothing has changed because I've not done any heat equation. I've done it for no steps. Let's do it for 10 steps and see what happens. And even in 10 steps, it's gone. I think it's already collapsed it to a point. So maybe I should do it for 1 step. And now with the plot, you can notice that it's already done something crazy to the mesh. So I mean, I took a very large time step. This is just a demonstration. Typically, you would want to take much smaller time steps than this. So let's do it not for a time step with each time step being 1 unit long. Let's do it for 0.01 units long. Okay, that means this delta t, which I set to be 1, I can't use that anymore. That means I will need to modify this equation, which is that. So I'll write delta t times, so it's going to show up here, delta t times L times un. So this is fine. So I'm going to have to set total time is 1, delta t is, let's say, 0.01, and I'm going to have to throw that in here. Okay, and let's try again now. So you notice that, is there a way to side by side plot? Maybe I should do. And let me put this all in one.
For side by side plot, we might have to translate the mesh.
Yeah, no worries. I don't want to do side by side. I will be happy to do the following. And let's plot V new. That's my V original, and that's my V new. Because I did only 10 steps, nothing much has happened. But instead of 10, now let me run it for one. I did only one. Let me now try 10 with this delta t. And now if I plot my V new, is there anything? That is weird. It shouldn't have collapsed that quickly.
Can we see the point in print the meaning?
Huh? Nothing has changed. Okay, so something went wrong here. No, I'm okay with doing this. There's a problem. This should be identity. I don't know what I was. Or maybe it was picking up an earlier version. So we knew.
Delta T is only the difference. Every time, so you still have the same difference. Yeah. You're not using it as a multiplier for the nth time step. It's not any delta.
It hasn't moved much, but the mesh is not being plotted. I don't know what is happening.
You could turn off the wireframe for a while.
Nope.
You could do a scatter plot.
PLT.scatter of just the V news of just the 0x.
And we have to use
Right.
3D scatter. We want to see something.
How do you do a 3D scatter?
Scatter 3D,
Okay.
and instead of this, shall I just add the link?
Yeah. If you want to come around, you can.
Yeah. And then it should work. Okay, let's scatter 3D. 3. Okay, fine. This will work. So yeah,
What happened?
these are the points that it has collapsed to now. This is the scatter plot.
But why did it collapse so quickly? And if I look at it here, it seems to have not collapsed, right? If I do difference, but that's
Yeah.
not very different.
Let me check anything. Maybe we could just plot the original points as well. See,
Yeah, but I
this is the original shape.
right. But why did it collapse everything like that? Whereas it's not collapsing here, right? If I look at VNU, it's not.
Yeah,
So I'm
but we're still looking at just 6
right.
points.
So I can look at
We could check the min or the max.
no, we could look at 20. Seems okay. I look at 50. Okay, something weird is going on, and damn, let's see if I can. Do it with
And what is the value when we did it for 1?
0. It should all be 0. It has not moved at all. Okay, there's some plotting issue, but I don't know how to resolve this in real time. So if I do it now for 10 steps, it's supposed to smooth it, but it is smoothing it. It's moving the vertices a little bit, but while plotting, I'm not sure what's going on.
I'm not sure why it is doing like this. And we just collapsed it to some few points.
But it's not collapsed if I look at the VNU. So
Yeah.
that's the problem.
This is negligible difference.
Right. And that's what I would expect with a 0.01 time step.
For 1, it was working, right? So maybe you could just see what difference we get for 1 time. I mean, delta time being 1.
Time being 1, delta t also being 1.
No, delta being the same as previous one.
And now I look
We had
at
seen that compressed, that
right.
So that is what I'm trying to see now.
Okay, so
And we'll have to add all those 3 lines.
yeah, but I can just plot this itself.
This is not the new one.
Oh, this is not the new one, but
oh, now it has plotted, right? Yeah, now it is showing.
now it's showing, but with many more steps, I don't know why it's not showing.
Maybe we just increment it by 1 more. See.
Let's try 5.
Yeah.
Okay, there's some spikes. Okay, the mesh I think is not consistently oriented. Usually when the mesh is not, there's some problem with the mesh, this happens. It's getting spiked by a crowbar, I think, and it's getting Yeah, this happens if I think the mesh has an issue, but at least in some parts where it's not, you can,
Maybe it could be non-manifolded.
it's not non-manifold. I think it's just an orientation or some issue like that.
Would normals play a role in this? So
No, orientation does, if it's not consistently oriented, the the triangles need to be consistently oriented. Otherwise, you can get some errors like this. Okay, that explains it. So let me try maybe one more thing to see if it works. Otherwise, I will have to stop without giving you a full like demonstration. So let's see what else is here. Let's try the cube to see if that does anything nice. So let's try the cube. Oh, it's a small cube. That's not going to work.
this here is
But sphere is not going to do much. Let's try the fertility. Okay, that's a nice. Hopefully the mesh is fine. Okay, and I'm gonna do that, and let's try plotting. Yeah, okay, at least this mesh you can see something. Yeah, there was something is wrong with the Cherubashka, but at least on fertility now we can try running it. I'm gonna clear this output.
you can delete this cell.
Yeah, but I don't want to delete it in case, that's why. And this cell I can delete. Okay, so let's now run it for some 50 time steps and see what happens. And I'll have wireframe. Even here it's starting to, even this mesh has some issues. No, the spy, I think we have seen this before too. It's like has to do with, yeah, orientations are poor. Let's try the hand. Hand is not off, is it?
So there could be a function read OFF file. I think
Maybe this itself directly
read
reads.
triangle mesh. You just have to change the function. Read OFF.
No, I think it is not OFF, it's MSH. It's okay. So maybe we'll try the bunny small. Let me not run it for 50 time steps. Let me run it for 10. So with this, there isn't much noise, but let me try adding some noise to this and then we'll stop. Okay, so v plus equals v dot random dot rand. Dot shape. And let me make it small. Oh, np dot random dot.
Maybe if you do rand in.
Yeah. That has no specificity.
Okay, just add a star before the shape.
Yep. Okay, that's way too much. Okay, so let's try smoothing this bunny and see if it gives me a smoother bunny now. Okay, if I did this and it's kind of it's already blown it out, I think. Even if I do it for one time step, what happens? It's not moved it much. Do it for 5.
I think this mesh does not have any holes in it.
Uh,
This image has some holes.
the bunny. Okay, no. So whenever you see these large things forming, it's because of some inconsistency in how the mesh has been specified. So sorry, folks, I can't. I should have checked what data was available in LIBIGL, but with this, there are data problems with the original meshes. But I'll still give you these code and see if I can clean it up over the weekend. It's not going to happen tonight, but I'll give you the code. We'll see if I can clean it up over the weekend. Yeah.
Because I remember the bunny mesh generally, this is stand for.
Yeah. Small.
It has holes near the bottom part.
Holes by itself shouldn't be a problem, but these things that happen are because of some inconsistency in how the mesh. I know, I understand, but you can still do heat equation and it will start collapsing the boundary also. It will move the boundary, it won't keep it fixed. But yeah, this problem is something else. So I'll try and give you what, okay, something for you to play around with. If you had like cleaner meshes, this would work better. I do have some cleaner meshes from other thing, but it's not in the off format and I'll have to try and load the vertex triangle mesh. So we'll stop here. I don't know if this online folks had any observations or comments. Perhaps not. Okay, so I'll share all the notes from today, the slides and the half-baked demonstration, and then we'll work with that, I think.